6. Discuss about triple day with a neat diagram. How is it different from day in terms of key size and number of rounds? Triple day, also known as 3DES or TDES, is a symmetric encryption algorithm that is widely used in various applications such as e-commerce, financial transactions, and electronic data exchange. It is an improvement over the original day algorithm that uses a single key for encryption and decryption. Triple day uses 3 keys to perform encryption and decryption in 3 consecutive stages, providing a much stronger security level than day. The plaintext is first encrypted with the first key, K1, using the day algorithm. Then, the resulting ciphertext is decrypted using the second key, K2, and the day algorithm again. Finally, the resulting plaintext is encrypted again using the third key, K3, and the day algorithm. The resulting ciphertext is the final output of the triple day encryption process. Compared to the original day algorithm, triple day uses a longer key length and more rounds of encryption and decryption. The key size in triple day is 168 bits, compared to the 56-bit key size in day. In terms of the number of rounds, triple day uses 48 rounds of encryption and decryption, while day uses only 16 rounds. This makes triple day much stronger and more resistant to brute force attacks than day. However, triple day is slower than day due to the additional rounds of encryption and decryption. To address this issue, the Advanced Encryption Standard, AES, was introduced, which provides better security than day and triple day with faster encryption and decryption speeds. 7. Use the Chinese remainder theorem to find an x such that x is defined as 1, mod 5, x is defined as 2, mod 5, x is defined as 3, mod 5. Also, if x cannot be found, state the condition and explain in detail why the solution cannot be obtained. To find the solution of the given system of congruences using the Chinese remainder theorem, we need to follow these steps. Step 1. Compute the value of m, which is the product of all the moduli. In this case, m equals 5x5 times 5 equals 125. Step 2. Compute the value of mi for each congruence. Mi is the product of all the moduli except the ith modulus. In this case, we have 3 congruences, so we need to compute 3 values of mi, m1 equals 25, m2 equals 25, and m3 equals 25. Step 3. Compute the value of mi for each congruence. Mi is the modular inverse of mi with respect to the ith modulus. In other words, it is the value of k such that mixk is defined as 1, mod mi. We can compute the modular inverse using the extended Euclidean algorithm. In this case, we have mi equals 1 for all I, since 25 by 1 is defined as 1, mod 5. Step 4. Compute the value of y for each congruence. Y is the solution of the ith congruence, which is given by y equals mix mi, x by, where by is the remainder in the ith congruence. In this case, we have y1 equals 25x1 times 1 equals 25y2 equals 25x1 times 2 equals 50y3 equals 25x1 times 3 equals 75. Step 5. Compute the value of x, which is the sum of all the y's modulo m. In this case, we have x equals 25 plus 50 plus 75, mod 125 equals 150 mod 125 equals 25. Therefore, the solution of the system of congruences is x is defined as 25, mod 125. If the moduli are not pairwise coprime, then the solution may not exist or may not be unique. In general, if the GCD of any pair of moduli is not 1, then the solution does not exist. This is because the Chinese remainder theorem relies on the fact that the moduli are pairwise coprime, which ensures that the modular equations are independent of each other. If 2 moduli have a common factor, then the corresponding equations are not independent, and the solution cannot be obtained using the Chinese remainder theorem. 8. Apply RSA cryptosystem for the given data. the public key of a given user is E equals 5 and the prime numbers assigned for P and Q be 7 and 13 respectively. What is the private key D of this user? If Callie wants to send the message M equals 13 to Alice by using public and private keys, calculate the ciphertext C for the given message M, and check whether decryption also yields the same message M. To find the private key D, we need to first calculate the value of the totient function, phi, n, where n equals pq. Here, p equals 7 and q equals 13, so n equals pq equals 91. Phi, n, equals p1, asterisk, q1, equals 6 asterisk 12 equals 72. Now we need to find a value for d such that d asterisk e, mod phi, n, equals 1. 5d mod 72 equals 1. One possible solution is d equals 29, as 5 asterisk 29 equals 145 and 145 mod 72 equals 1. Therefore, the private key for this user is d equals 29. To encrypt the message M equals 13 using Alice's public key, we first convert the message to a number using some agreed-upon encoding scheme. Let's assume we're using ASCII encoding, so the letter M corresponds to the number 77. The ciphertext C can then be computed as follows. C equals M caret E mod NC equals 77 to the power of 5 mod 91 C equals 78. So the ciphertext is 78. To decrypt the ciphertext, Alice can use her private key as follows. M equals C caret D mod NM equals 78 to the power of 29 mod 91 M equals 77. We get back the original message, M, which is 77 in this case. Therefore, the decryption yields the same message as the original message, and the RSA encryption decryption scheme is successfully applied. 9. Alice and Bob use the DIFFIE-HELLMAN key exchange technique with a common prime Q equals 71 and a primitive root alpha equals 7. A. If Alice has a private key XA equals 5, find her public key YA. B. If Bob has a private key XB equals 12, find his public key YB. C. What is the shared secret key, K, between Alice and Bob? A. Alice's public key YA equals alpha caret XA mod Q equals 7 to the power of 5 mod 71 equals 49. B. Bob's public key YB equals alpha caret XB mod Q equals 7 to the power of 12 mod 71 equals 55. C. The shared secret key K is calculated as follows. Alice computes K equals YB caret XA mod Q equals 55 to the power of 5 mod 71 equals 29. Bob computes K equals YA caret XB mod Q equals 49 to the power of 12 mod 71 equals 29. Therefore, the shared secret key K is 29.